Hi, welcome to Mrs. Ogram's Maths. This video is going to take you through the Probability Concepts paper, the external paper for Level 3 from 2017. Okay, so question 1, we've got a sample of 996 students from years 9 to 13, and we've got some information about the languages that they speak and whether they were born in New Zealand or not. Now we're looking at whether they can just speak one language or they can speak at least more than one language fluently. Okay, so first thing we want to calculate is the probability that the student can speak only one language. Okay, so they can't speak more than one. So the easiest way to approach this is to try and put that information into a tree diagram. So we've got either they were born in New Zealand or they weren't, and those two probabilities have to add up to 1. We've got 78.4% from the information given above, and then just take it away from 1 for those not born in New Zealand. Okay, then of each of those groups, we want to know their chances of being able to speak more than one language fluently. So we've got those two branches for more than one language or just one language. So of the ones that were born in New Zealand, 35.6% can speak more than one language. So we've got 0.356 there, making this one 0.644. And of the ones not born in New Zealand, we've got 0.698 can speak more than one language, which gives us 0.302 can only speak one language. Now calculate the probability that the student can speak only one language. Okay, so the two portions of our tree diagram here are either this branch or this one, where it comes out to just one language. So the probability of that first branch is 0.784 times by 0.644. And then we're going to add the second branch, which is 0.216 times by 0.302. And that comes to 0.57023 significant figures. Okay, so the test for independence is that if you found the probability of one event and the probability of the other and multiply them together, that would be the same as if you found the probability of both those things happening together. Okay, so we're going to test that out. So from the previous slide, we had the probability that a student was born in New Zealand was 0.784. We'll call that event A. So then event B would be the probability that a student speaks more than one language. Well, we just worked out in the last part the probability that they speak only one language is 0.570. So if we take that away from 1, we will get to what this should be equal to, which is 0.43. Then next is to find the probability of both things happening at the same time. So born in New Zealand and can speak more than one language. If we read off the tree diagram we made before, we get that to be 0.784 multiplied by 0.356, which gives us 0.279. So then we do our test for independence. So the probability of A times the probability of B will come to those two things multiplied together, 0.337, which of course is not equal to the 0.279 of probability of A and B. Therefore, these events are not independent. Okay, so we've got some information here on students and whether they own cell phones and have Facebook and if they're male and female. Okay, so calculate the probability that the student is female and does not own a cell phone. So we've got female and does not own a cell phone. So that's this 52 here. So probability of female and no cell phone is equal to 52 out of 996. So the next part asks us to look at the events whether having a Facebook account and owning a cell phone are mutually exclusive. So mutually exclusive means they can't happen at the same time. So we want the probability of both of those things to come to 0. So F and C happening together, Facebook and cell phone, would have a probability of 0. Now, if we have a look at our tables, we can see that has a Facebook account and owns a cell phone here has got a number in there. So we were testing for if that's equal to 0. It actually equals 750 out of the 996 students. Therefore, it's not equal to 0. Therefore, they are not mutually exclusive. And the last part of this question is asking us, given the information that 349 of the students here were male, had Facebook and a phone, then what's the probability that a female doesn't have Facebook and doesn't have a phone? Now, there's a lot going on here, so we want to try and simplify that information. We've got 3 things that we're looking at: gender, Facebook, and cell phone. So we can set this up as a Venn diagram with 3 circles on it. So from our first table, we've got that they are male. We could just as easily write that as female. But this total for male is that we know that that will come to our total here of 408 plus the 55. So 463 altogether. Then we need a circle for Facebook. And we know that the total number of people that have Facebook we can get either from those 2 added together there, or from these 2 added together. Either way, it comes to 814. Which leaves our third circle for cell phones, where we can add up the cell phones here, or where else was it? Owns a cell phone here, which comes to a total of 889. Okay, now this 349 that we're told, that's male, has Facebook, has cell phones. So that's where all of these overlap in the middle. So that's 349. Okay, now we need to work out how we can fill in the rest of the pieces. So I'm going to start with this bit here. Now, the bits in the middle are probably going to be the easiest to work out because we already have a piece of them. We've got that 349. So this section in the middle is going to be all of the males that also have Facebook. So male and has Facebook comes to a total of 381. Now we already have 349, so the bit left in this portion here will be what we need to add up to 381. So that comes to 32. Now I'm going to do the same thing with the males who have cell phones. That has to add up to 408, and we've got this section here has got to add up to that 408 total of all males who also have a cell phone. We've got 349 that have the cell phone and the male, and they have Facebook. So if we take that away from the 408, we'll get what's left. And that comes to 59. And you can see where I'm going to go next is that other middle section. So the 349 plus something will make our total of all the people that have Facebook and cell phone together. So if we look at this middle section, Facebook and cell phone, that needs to come to 750 in total. So take off the 349 and we will get 401. So then all that's left to do to fill in the rest is take these totals that we know each circle has to add up so that we can work out the bits that go in the gaps. So we get 23 males that don't have Facebook or cell phone. We get 32 people that only have Facebook, they're not male and they don't have a cell phone. And then we get 80 that only have a cell phone, they're not male and they are not on Facebook. Now at this point we can calculate the probability that a student is female, does not have a Facebook account and does not have a cell phone. That means they're not in any of these groups. Now I'm running out of room a little bit, I'm going to have to overlap, but we have our outside set of all of the people in this group, and we knew that there were 996 of them. So if we add up all of the numbers of people that we've got in our Venn diagram so far and take it away from 996, we'll be left with 20 people that are left over that aren't in any of those groups. So for female, does not have Facebook and doesn't have cell phone, that's going to be all the people that don't fit in that group. So the chance of picking that person is 20 out of 996 is the probability that we're looking for. Question 2 is about some flights and whether they're with Air New Zealand or not, and whether they were delayed or not. Now, if you get a bit of a gap in your question, that usually gives you a clue that they're expecting you to draw something up. So it could be a tree diagram or a Venn diagram or a table. So let's try put this information into a table. I think will be the best way to set this out. So we're going to look at they are either with Air New Zealand or another carrier, or that they're delayed or not delayed. So we are told there are 83 in total altogether. 64 were by Air New Zealand, 31 were delayed, and 12 flights that weren't operated by Air New Zealand were not delayed. So that's other and not delayed. So that's 12 in there. From there, we should be able to fill in the rest of the information on the table just by working through those totals. So 83 minus the 64 means that there are 19 flights with somebody other than New Zealand. The 19 minus the 12 gives us a 7 for the other flights that got delayed. 31 minus the 7 will tell us how many Air New Zealand flights were delayed. So that's 24. We've got 64 minus 24 will give us the Air New Zealand flights that were not delayed. And then 40 plus 12 will give us 52 total that weren't delayed, and we should just double check that the delayed and the not delayed, the 31 and the 52 adds up to the 83, so we haven't made any mistakes along the way. Okay, now calculate the probability that this flight was delayed given that the flight was not operated by Air New Zealand. So we are only looking at the other category. We are only considering that we're already restricting down to given that the flight was not operated by Air New Zealand. So we're looking at a total of 19 flights, and the probability it was delayed, that's 7 out of 19. Okay, so now we want 2 reasons why we should take care if using this data to predict the flights departing from Wellington Airport. Okay, so number 1. You can have different circumstances on different days. So if you get extreme weather conditions on one day, it'll have a much higher chance of experiencing delays than a fine, sunny, clear day that all the flights can take off as planned. You also might get different fluctuations in the days of the week as well. You could talk about that as being a different circumstance for the different days. So you would expect weekends to be busier and potentially more problems because there's more people coming through and might cause more delays. The second point I'm going to make is that the amount of data we had was pretty small. There were only 83 flights in it. So extrapolating that out to larger sets of data can be unreliable. Now we have 2 events. A is that the flight's departure time is affected by passenger behaviour, and B is that it's affected by weather conditions. And of course you could have it affected by both as well. We're given some information about different portions of those overlaps, intersections and what have you. So I'm going to set this up as a Venn diagram to try and see what's happening. Okay, now let's take the information we've been given and try and pop it on there. So first of all, we've got that the union of A and B is 0.54. What that means is that all of this area here that's in either A or B will be 0.54. Now, let's see if we can make this a little bit easier. If I set up some letters in there, so section A, B and C, then A, B and C will all add up to 0.54. Now, since the whole of our Venn diagram has to add up to 1, then anything outside, let's call that region D, A, B, C, and D, they've all got to add up to 1. So if those 3 inside of the circles add up to 0.54, then it leaves outside of the circle as being 0.46, so that it adds up to 1. Okay, then the next bit of information we're told about is this. The union of A dash and B equals 0.86. So that means that everything that is not in A, so let's shade that in first. So all of this section here that is not in the circle of A, so that takes care of this one, or it is contained in B. So that's everything here that's in the B circle. That's got to add up to 0.86. So those were the regions B and C and 0.46. They have to come to 0.86, which means that B plus C must be 0.4, and B plus C is all of B. So the probability of B is 0.4, which is the thing we were looking for, which is the flight's departure time is affected by weather conditions. Right, part B is some AI program that predicts gender based on a sample of writing. Okay, so calculate the percentage of the predictions that were correct. So the computer correctly matched up the actual gender with the predicted gender. So that will be anywhere that these match up. So female and female, male and male, add them together. So we've got 172 plus 94 out of our total of 400, which comes to 0.665. We've been asked to do it as a percentage, so just simply turn that into 66.5%. Okay, now we need to evaluate how good this model is and identify potential issues and do some calculations for that. So I would look at something along the lines of how accurate is this for each of the gender groups? Is it over predicting females or males, for example? So if we take a look at the females, the number of those that were correctly predicted is 172 out of 198, which gives us a 0.8687. But for the males, we only have 94 correctly predicted out of 202 in total, and that gives us a success rate of 0.4653, which is quite a difference between the two gender groups. So I would say the potential issue here is that it's more accurately predicting females, or perhaps over predicting on the female side of things, and not balanced out well for the males. Question 3 is about strep throat and the effectiveness of a particular kind of test and whether it produces positive or negative results. So part 1 is that we have 298 primary school children who have sore throats. And then we've got the results of whether they turned out to have strep throat or not, and whether the RADT test showed them positive or negative. Okay, a website offering health advice says that most sore throats for children are not strep throats. So remember, everything in this table is from children that had sore throats. Now we want to find out how many of them had sore throats but didn't have strep throats. So that's these two numbers here. So 0.124 plus 0.671 comes to 0.795. That's easily most. It's definitely more than a half. So we can say that, yes, this data does support that statement, that most sore throats are not strep throat. Question 2 is asking us to put the information onto a tree diagram. So we just worked out in question 1 that there was the chance that they didn't have strep throat was 0.795. So we'll write that on straight away. And then, of course, that they do have strep throat, those two branches have to add up to 1, so we'll get 0.205. Now the next bit's a little trickier, and I expect a lot of people did this wrong and just simply wrote the numbers from the table on, but we're talking about conditional probability for the next step. So that top branch is what's the probability that they had a positive test result given that they had strep throat. So for that, we are only looking at the people that had strep throat. We're restricting it down to only considering those, and the positive results were 0.074 out of that. So it's 0.074 out of 0.074 plus 0.131, which comes to a total of 0.205, which is 0.361, and that goes just here. We'll do a similar thing for the other branches. So had strep throat, negative result, well, they have to add up to 1. So this bit here will be 0.639. Now, didn't have strep throat and had a positive result, so we're looking at this group here. That'll be 0.124 divided by the total of 0.795, which comes to 0.15597. So we'll round that up and it will be 0.156. Those last two branches should add up to 1, so this will be 0.844. B is about a game involving spinners, and we've got the scores from 50 games here. Now the score is calculated as the median of the 3 spinners. Calculate an estimate for the probability of gaining a score of 1. So this is a real nice and easy, straightforward probability. From these 50 games that we've got here, how many came out to a 1? Just count the dots. There's 7 of them, so it's 7 out of 50. Now we're asked to count the theoretical probability of that score of 1 happening. So we've got 3 spinners that I'm going to represent with 3 blank lines. We need the median to be 1. So the middle number of those 3 spinners has to be 1 when we put them in order. So now if we think about the possibilities that we could have, and the easiest thing is probably just to list them, even though it's a little bit tedious. List all those different possibilities. So we could have 1, 1, 1. That would give us a median of 1. We could have 1, 1, 2, 1, 1, 3, 1, 1, 4. And then we'll move on to the others. For us to continue on having a median of 1, we're going to have at least 2 ones of the 2 spinners land. So 2 of the spinners would have to land on a 1. So we could also have 1, 2, 1, 1, 3, 1, 1, 4, 1. And then 2, 1, 1, 3, 1, 1, 4, 1, 1. So there's our total ways we could do it. So this is 10 ways to get what we want. And we need to put that out of all the possible spins we could have. So for that, we need to think about on spinner number 1, there are 4 numbers we could do here. There are 4 we could get on spinner number 2, and there are 4 we could get on spinner number 3. So total ways would be 4 times 4 times 4, which is 64. So our probability will be 10 out of 64. Okay, now this part 3 is asking us to put the theoretical probability, work it out for 1, 2, 3, and 4. So we've just done it for 1, came to 0.156. Now, having a think about the nature of this game, this probability distribution will be symmetrical. 4 will be able to be done in just the same sorts of ways that we were able to get a 1 that we saw on the last thing. So that will also have the same probability, 0.156. You can go through and list them and check and make sure, but I'm just trying to do this in a slightly more efficient way. So 2 and 3, similarly, because of the symmetry of this distribution, whatever this number is here, it will be the same for 3. Now we know that those probabilities all add up to 1. So if we do 2x plus 0.156 plus 0.156, that will add up to 1, which tells us how much x will need to be. So if we work through that, we'll get 0.344. Now, if you didn't manage to follow along with that, it's fine. You can go through and list those probabilities as well to work out the chances. It just will take you quite a bit longer. Okay, so that brings us to the end of working through that paper. All I need to say now is good luck and subscribe.